All right. Good afternoon, everyone. Thank you for coming to today's RAL seminar. Very pleased to introduce our speaker from our very own RAL, Dr. Cindy Vale Castro, and who's become well known around here. And she's working on our ASP postdoctoral fellow as part of the Hydrometeorological Applications Program, and also with the National Security Applications Program. And so, as many of you know, she's made a home for herself, being a sought-out collaborator for many of us with her skills in hydrology, GIS, and spatial mapping and stakeholder partnerships, among other areas. Going back, her educational background includes a bachelor's in civil engineering, which she did at Texas A&M University, finishing up in 2011. And from there, she went on to work in the real world in civil engineering as a licensed civil engineer, and had a lot of really interesting experiences working for the Department of Hydrology and Hydraulics in Houston, serving as a project manager for AECOM's technical services and engineering work in Ghana, and so many other experiences that I won't go through, but definitely a lot of really interesting experience that she brings to the academic community. And then in 2016, she finished up her master's degree in civil and environmental engineering at the University of Texas, Austin, and then finally got her PhD in the same field, but at the University of Houston in 2021. And prior to coming here was at the University of Illinois, Urbana-Champaign, and we're glad to have her here now. She lives just right up the road in Longmont, has 3 boys, and husband who's a firefighter who also previously comes from the engineering field, so a very interesting background. Very pleased to have Cindy here.
Hello? Hello? It's working? Okay. Yes, thank you for that intro. Where did you find all that information? I didn't send that to you. Okay, thank you for the kind introduction. So yeah, my name's Cindy, and I'm a second-year postdoc, and today I wanted to talk about I broke it. Okay. Some of the research that I proposed in my ASP application, I was specifically interested in better understanding space-time scaling effects in watersheds that have been influenced by humans. And so we'll be looking at how we can use scale theory to reduce uncertainties in low-impact development performance for urban hydrology. So first, what do I mean by low impact development? So this term has been around for a long time, and it's come to mean basically any kind of engineered storage feature that will hold water in place in order to make the runoff be temporarily retained so that it doesn't go downstream as fast. So the whole intention of low impact development is to offset when we add increased impervious cover, like parking lots or roofs or buildings. But back in the day, it started predominantly as detention and retention ponds back in the 70s and 80s. And over time, it's grown to include these more disaggregated features like green roofs and rain gardens. And so a lot of low impact development features use native vegetation as a way to provide that storage and retention property, but not all of them do. So you can see like rain barrels, permeable pavement, those definitely don't use nature. But I wanted to include this definition here because it will become important later on as we look at the scaling theory. So in my study, LID means any set of engineered storage features which are designed to mimic the natural water cycle by temporarily retaining stormwater runoff prior to being released back into the drainage system. And this contrasts sharply with traditional stormwater infrastructure, which we call gray water infrastructure, such as pipes or gutters or channels. And these are designed to get water offsite as fast as possible. And the problem with relying solely on gray water infrastructure is if every new development sent the runoff as fast as possible, then downstream your peak flows will start to aggregate and your flood risk is increased. And I also like to show this slide because I get a lot of questions about the nomenclature. So as mentioned, low impact development first started being the primary term used to describe this type of stormwater mitigation solution in the 70s. It was after World War II, when there was large urban sprawl all over the United States, that developers started mandating we need to retain stormwater runoff specifically from neighborhoods. So they used detention and retention ponds. Over time, it became to include more green features, and the terminology kind of all means the same thing, but there's small differences depending on where you're located in geography. So in Europe, they use slightly different words than we use here, and the breadth of ecosystem services provided. But for purposes of our study, we'll just call everything LID under the same umbrella. And when we do bring in those nature and vegetative components of LID, there's a ton of research showing that there's many environmental co-benefits in addition to reducing the stormwater runoff. So when we have more vegetation, it's been documented to reduce urban heat island effects, can create and connect different habitats, especially in really densely populated urban centers, absorbs noise pollution, captures greenhouse gases, and then a big reason it's used is because it can filter water before reaching the outlet. And then there's also a lot of research into the social co-benefits. Much of my PhD research was over this part and how there's a lot of documentation that when we have more access to nature, when we're in urban environments, it can improve our mental health. It's been shown to decrease depression, post-traumatic stress disorder, improve physical health issues like cardiac arrest, morbidity, asthma, diabetes, et cetera. But all of these benefits are only found when we have enough of them. So if we just have one green roof, we're not going to realize that much benefit, right? But when they're spread out and they're really distributed, we've been shown to have these kinds of things. But despite these environmental and social co-benefits, unfortunately, the adoption trends of LID solutions has remained pretty stagnant over years, and the literature supports this. There's a few cities where this is an outlier. So Beijing is one of them, Philadelphia, Washington, DC, they're really greening their urban centers, but that's the exception to the norm. So this is a chart from Houston, where I'm from, and it shows our expenditure in traditional stormwater infrastructure compared with urban LID solutions, and it stayed pretty stagnant over time, despite the research into urban LID infrastructure skyrocketing, especially in the last 15 or 20 years. The research into LID has grown approximately 30% year over year on average, but stakeholders are not really adopting it en masse like we would hope. And part of the reason for this is because there is a lot of performance uncertainty in the scientific literature about how well these features can, in fact, reduce peak flows downstream. So here's an example on the left from Emerson et al. In 2005, where they studied over 100 real-world detention ponds in a Houston watershed, and they analyzed before the detention ponds were built versus after for 2 to 100-year design storms, which are pretty strong storms. And they found almost zero change in peak flow downstream. So 100 ponds, and it didn't really change anything. Under some of the design storms, they got like about 0.3 reduction in peak flow, 0.3%. But some of them, they found that the detention ponds actually made conditions worse. So flooding went up downstream. But those are for pretty strong storms. Here's another study by Lim and Welty in 2017, where they were in Washington, DC, which does tend to have a lot of urban greening and LID features. And they looked at smaller, more variable storms, and they wanted to see, okay, maybe it's the placement of the LID in the watershed. So let's test 9 different spatial configurations and see if we can increase our efficiency. And they also found about 0% peak flow change between those 9 different spatial configurations. And so, but then when you look at other studies, where you put LID in the watershed has a huge impact. So in the top, this is also in Houston, same climate conditions, and they found if they put LID near the outlet, flood risk was substantially improved by like 20% in this study. So peak flow went down. And then another study on the bottom where they moved lid all over the watershed and they assessed what would happen. And they found that the downstream area was the worst location to put lid, and it made flood conditions worse. And so if you look at this type of literature, you'll see these kinds of conflicting results all over the place. And this is summed up in a lot of recent meta-analyses. This is one of the largest ones I could find, where they looked at over 2,700 lid case study papers. And as you can see, the peak flow control varies widely depending on where you are, what kind of storm you're assessing, and what kind of feature you're using. So from 5% all the way up to 100% change. And what they concluded in this meta-analysis is that the performance of lid systems is significantly impacted by the size of the storm event. So that makes sense. Stronger storms may be too much water for this little bit of grass to do anything about. So it includes how long the storm is, the event duration, and its peak intensity. But also that spatial distribution of lid throughout the watershed plays a role sometimes, and sometimes it doesn't. They concluded there is no consistent pattern emerging across all of these case studies for when the storm controls your outcomes and when location controls your outcomes. So what they suggested, and I've seen the same suggestions in a lot of these meta-analyses, is if you're going to use lid, just always design for smaller storms and always just distribute them everywhere that you can, distribute them heterogeneously. So this becomes a problem for real-world adoption and stakeholders, because they might think, if I can only get a 2-year storm out of this, my cost-benefit ratio is not going to be very good. I might as well just rely on traditional stormwater infrastructure, because I know that that will tend to work better. And if I'm going to have to place it everywhere, I might spend too much money. And determining when each of these would occur in your locale, really zoning in and figuring out the optimal solution for your watershed, often costs over $1 million or several $100,000 to hire an engineering firm and run these models and figure out if it's going to work in your location. So they don't want to have to spend the money just for a firm to tell them it will not work. And so a lot of times they skip over this process completely. And why do we care about peak flow performance specifically? So this is an excerpt from the Harris County Flood Control District design criteria. This is in Houston, but there's similar design criteria in many municipalities across the nation and the world. And when you're using lid or any kind of stormwater mitigation infrastructure, you need to show that in your design, the post-project condition will have a peak flow equal or lower to that of pre-project conditions. You have to demonstrate if you stick a Walmart parking lot somewhere, you're not going to flood your downstream neighbor. It's a legal issue. So they build these into most design criteria. And if you can't demonstrate this, you're not going to get it through regulatory requirements, and you cannot get the permit to build your development. So we really need to understand if lid can impact peak flow, how and when. And then if you look at the literature, there's a lot of studies that show stakeholders being interviewed in real-world interviews and asking them, are you adopting lid? And if you're not, what are your major barriers? And the top words that tend to show up across the top 150 papers on lid barriers is shown on the left. There's a lot of barriers. People don't understand how to maintain them. That's a big one. Finances is a big one. But one that tends to show up over and over and over is lack of planning, lack of technical knowledge, and uncertainty in the design. So that's one of the top 4 barriers to lid uptake. And then when you survey the same stakeholders and ask them, well, what would it take for you to start adopting lid features within your locale, they say better stormwater planning, better knowledge. So they want to be able to look to the science and say, you guys can give us some kind of recipe that tends to work everywhere and we can understand, otherwise we're not going to trust it. And I saw this in my personal experiences whenever I was working in Houston. So in 2011, I started at AECOM as a consulting engineer, and we were tasked with designing the first LEED certified, what would we call it? Sporting facility, I think, in Texas. And so this is the tennis courts for Rice University. They hired AECOM and they wanted it to be green. And it was a really big deal. It was going to be a showcase for the whole state that green can work. And we spent about 1.5 years on the design. We worked with permitters, we worked with regulatories, we worked with all this stuff, and we could not show that the peak flow was going to reduce. It ended up costing them more money than it was worth it. And Rice University, even though they're very environmentally oriented and progressive, they decided to scrap the green component of this project and move forward with traditional gutters and ditches for their tennis courts and parking lots. And so then whenever I came back to the Houston environment much later during my PhD in 2021, I had the opportunity to work at the city of Houston in their sustainability group. And I thought, oh, in 10 years' time, surely this problem has been fixed. And it has not been fixed. And this opportunity was actually interesting because as part of the sustainability group, we were on many different task forces where we connected with sustainability city leaders across the nation and across the world. And we would have meetings all the time and ask them what were their barriers to green infrastructure and if they were adopting. And this didn't seem to be just a Houston problem. This seemed to be a problem by many city leaders, and they were expressing frustration about not being able to push it through to final implementation. And then as part of my PhD and last postdoc research, I interviewed some of these stakeholders in Houston to get a better understanding of their reluctance to green infrastructure. The city actually spent a lot of time and money developing this incentives manual for green development. Houston's unique in that we can't tell developers what to do. We can just encourage them because we don't have zoning laws. But we tried incentivizing them by reducing their permitting costs and telling them that they could get their project through the door faster. We would fast track their permitting, and for developers, time is money, right? And we would give them a pretty trophy, and they could have awards on our website, and it didn't do anything. Developers were like, no, we're not taking your push for green development. And in these meetings, yeah. Surprise. So I kept seeing the key barriers over and over as they kept saying, well, we read some of these papers I referenced earlier, and we don't think it works in Houston. It won't even work for a 2-year storm. Why am I going to bother? So they had this mistrust of performance, and their mistrust kind of trickled into a low public buy-in, and so clients were not pushing for this kind of thing with their projects. So we really need to bridge this gap between scientific uncertainty and performance in the LID world to really push it forward. So in 2020, a paper was published in 2020 called Assessment of Climate Sizing and Location Controls on Green Infrastructure Efficacy, a timescale framework. And this was a really interesting attempt at describing why this uncertainty occurs, why you get different outcomes under different locations, different climate settings, different designs, through the lens of raw hydrological scaling principles. And so in this paper, they demonstrated the importance of some scaling ratios, which you'll see on the X and Y axis, and we'll go through momentarily. But from these scaling ratios, if you can know those ahead of time, you should be able to place your watershed and your theoretical lid design before doing any robust modeling or anything into one of these regimes, and it will tell you, is the storm going to drive your output? Is it a trivial storm? And you can probably get a pretty good performance because the storm's so low compared to your storage. Is it a major storm and nothing's going to happen? Or does location matter, or does it not matter? And so I read this paper during my last postdoc, and it really inspired me. But to be honest, I didn't really trust it. I thought it was too simple. So that's what my postdoc research here was doing, was assessing this framework to see if it's real and if it works. So as mentioned, they demonstrated the importance of ratios between 3 critical scaling variables. So the first one is the time of concentration. The time of concentration describes how long it takes for once water falls anywhere in the watershed to reach the outlet. And that's important because that tells you how much water is going to come, how big your drainage area is, how fast stuff's flowing, if it's a really steep slope or fast slope, flat slope, etc. They also looked at the storm duration time. So essentially, how long is your storm? How long did rain fall above some threshold? What's your lid storage time? So how long does it take for all of your lid features to fill up and start spilling over? And that spillover becomes part of your urban runoff again. And this lid storage time is a function of your volume. So that's the engineering parameter, how big you're going to put everything. Your area treated. Are you going to treat all the parking lots or just 20% of them? And the intensity of your storm. So they built this theoretical framework, and if you know these 3 timescales and you know their ratios, theoretically you should be able to place your case study within one of these regimes. The trivial storm regime is when your TR ratio, which if you'll remember, it's your storm duration over your storage time. So the storm is longer than it takes for all the lid features to fill up. This implies a small storm, where all the treated runoff should be fully detained by your lid storage, and lid can reduce peak flow irrespective of its location in the watershed. If you fall within the location relevant regime, this is where your times of concentration kind of start to synchronize from the overall watershed time of concentration versus the one where you stuck all your lid features. And so where you put them will drive your runoff. So location controls performance. If you're in the location irrelevant regime, runoff will reach the outlet before the lid becomes full because you have a really fast time of concentration here. So lid can reduce QP irrespective of location as well. And then if your storm is too long and too intense for your available lid storage, then you have a major storm and no peak flow reduction is possible. So this idea of hydrological regimes came from some classical scaling theory in the literature. We know that different hydrological processes are driven by different spatial and temporal scales, and what their spatial and temporal scales are doing and how they're interacting will tell you which processes are driving the outcome. And from my understanding from doing the literature review, starting in about the 50s to the 90s, there was a lot of research devoted to kind of classifying these different scale interactions. And the goal then was, if we can understand these core underlying processes purely from a theory of scale, then we can translate stuff from gauged catchments to ungauged catchments. However, a lot of this research kind of trickled off in the late 90s and early 2000s when we got better data and higher resolution computing powers. And so we still looked at scales, but it was more on the sense of how big or small does our data need to be, and not as much, at least in hydrology, on the underlying hydrological principles. And so this paper is an example from 1997 of taking these different scale interactions and plotting some hydrological regimes. This paper was the inspiration paper for the one I just walked you through. And in this paper, they took some dimensionless scaling ratios. You can see it's tiny on the bottom, on the 2 axes. They did the same thing. They took 2 timescale ratios. They said, wherever you fall within these regimes, you'll know what's governing your hydrological behavior. So in this paper, it was either seasonality of your storm or within storm variability patterns. That's what's going to drive. However, a lot of this hydrological regime scaling research in the 1900s, in the last century, were all based on natural catchment hill slope theory. And as we know, urban catchments operate very differently. So if we start as engineers forcing little buckets of water throughout our urban catchment, it's going to change our runoff, and we can no longer rely on the underlying process controls we've developed previously from natural hill slopes. So this 2020 paper was a novel attempt to translate this type of thinking into urban watershed hydrology, but I thought it was too simple, and so we'll go through how we assessed it. So in that previous paper, they used a very rudimentary bucket modeling approach. It's the very simplest way of doing hydrology. And you just have a bucket where precipitation can come in, you run some numbers, and runoff comes out. So in their study, they didn't take into account infiltration effects, they didn't take into account evapotranspiration, they assumed the entire watershed was impervious, and you just stuck one block of lid on it. So impervious and pervious features didn't intersperse. They didn't disaggregate the lid features and that kind of thing. So to me, the way they did the bucket modeling and proposed a simple framework, that's good for looking at macro scale heterogeneity patterns. So they did kind of a top-down analysis. But coming from an engineering background where you really need to show all of your detail and you get different results, the more detail you bring in, I wasn't sure if a bottom-up analysis would show the similar results. So I wanted to see if we look at the same concept from a top-down approach and a bottom-up approach, is there going to be scale and variance in the middle? And if there is, then that suggests these are indeed universal scaling laws and not just an artifact of the bucket model that they built. And it's okay that I'm saying this because I worked with these authors on this paper and they know that it needed to be validated with real world data. So this is what the updated rainfall runoff model that I built to validate the framework looks like. The actual equations are not that important for this presentation, but just to demonstrate that we used very robust equations. It's a pretty strong model. And so we used nonlinear reservoirs, which would make the storage discharge dynamics in space. I brought in distributed infiltration and runoff effects. I brought in heterogeneous landscapes using land cover, the lid was spread out, the slope, et cetera. And I counted overland flow effects. In their study, they didn't count overland flow effects. They assumed that it was negligible over the entire time of concentration. They just looked at the channel network. In some watersheds, that's true. But in Houston, being so flat, you really have to understand how long it takes for water to go over the land. And so I put all of this in an EPA SWMM model, which is the gold standard for modeling lid, and studied this case study in Houston of the White Oak Bayou watershed. And so the White Oak Bayou watershed, it's a densely populated urban watershed in Houston, and it has a long history of flooding. And they've put millions and millions and millions of dollars of traditional stormwater infrastructure in here, and there's still a flooding problem. So there's been a lot of calls to kind of complement these gray water infrastructure with some green features, but it hasn't happened yet due largely to this performance uncertainty. So I studied this watershed. This is what the model configuration looks like in SWMM. It was a little over 211 square kilometers in area, so it's quite a big watershed. And I subdivided it into about 155 subcatchments. I calibrated and validated it using local stream and rain gauge data over the course of 2 years of data and got a baseline model. And then I started adding in lid features to see what would happen to their performance. So in each of my designs, I added about 35,000 individual lid units. I modeled rain barrels because they made the TS timescale the most easy to understand. I didn't want to convolute it by adding vegetation, but technically you could have modeled a vegetative rain garden as well for this in SWMM. But I put 35,000 rain barrels. It came to about $1.5 million, which is actually a reasonable expenditure in this size of a watershed. And I wanted to see what would happen if I placed lid in these 7 different colored sub-drainage areas. So if we congregated most of our 35,000 features downstream, midstream, or upstream, what would happen? When does location play a role, et cetera? And then I ran this model over a set of engineering design storm events. So in stormwater engineering, it's very common to use synthetic design storms so that everybody's running the same thing at the same time when they're trying to prove if their infrastructure works or not. We typically use these intensity, duration, frequency curves from NOAA Atlas 14 data, and we translate those into hydrographs. And so as you can see on the right-hand side, when you translate these curves into hydrographs, most of your rainfall is going to be congregated in the middle of the storm. So it's synthetic, it's not real world where it's varying. But this is the gold standard, and if you want to get these lid things approved, you have to demonstrate that they'll work under design storm conditions. So I analyzed my lid designs for the 2 through 100 year return periods over 7 different storm durations from 3 hours to 36 hours, which is pretty standard. So with 42 design storms and 7 different lid designs, it came up to a little over 300 SWMM models that I was able to then plot in the scaling framework and see if it worked or not. So here's the results of where these 300 some odd models fall within the regime states. And in comparing what was actually happening to the peak flow in my model and where it fell on this chart, I would say the framework was about 95% effective in estimating the storm and location controls and whether or not peak flow could be reduced. The instances where it was not effective, I tended to have some of the model outputs fall within the location relevant regime, when in reality they fell closer into the location irrelevant regime, so it was conservative. There's a few instances where it said, maybe you should optimize your design by moving the lid features, and really you didn't need to. It would have worked equally well anywhere. But everywhere else, it tended to match what the bucket model framework suggested. And so I did this by calculating all of those characteristic timescales for all of the 300 some odd models. And here's an example of the output for that. So you can see the 2 through 100 year storms, and then our TR, our storm duration timescales on the bottom, 3 through 36 hours. These column bars is the lid storage timescale, TS. So it takes longer for them to fill as the storm gets stronger, of course. And then the time of concentration is these red dots. It tends to be around 8 hours, but it varies a little bit depending on storm intensity. And so if you recall what our regime looked like, we can start to look at these timescales and say, okay, when I have, for example, the lid storage time is much, much smaller than both the time of concentration and my storm duration, I should fall within trivial storm, right? And we can start to ask these same questions if my storm duration is way longer than my lid storage time, I should fall within major storm, right? And so I started to estimate initially, but then I had to open all the SWMM models and check the peak flow changes and actually verify if this was working. So to do that, I created this lid efficiency index because this framework, while it will tell you if lid will work or not, it does not tell you the extent to which it works. Will it give you 10% better results? Will it give you 50%? You do not know. So the novel part of the new paper was that we proposed this efficiency index that would help you turn it more into an engineering percentage. We normalized by precipitation so that we could compare many different types of storms to one another and compared them with the models, and indeed what was in the scaling framework and what was happening in the actual hydrological model tended to match up. And so here you can see an example of where the green, location irrelevant, and blue, location relevant, start to kind of coalesce and come together. So I just wanted to walk through an example of what that would look like in case that doesn't make sense intuitively. So here's an example where location did control the day. The 10-year, 6-hour design storm was location relevant. So on the top, we can see the design storm hydrograph where your rainfall is coming down. The black dashed line are our baseline conditions. So this is our runoff downstream without any lid features. And then if we were to place lid in drainage area 2, which is kind of downstream, this yellow shaded region, we'll get some some peak flow reduction of about 8.5%, but we don't get nearly as much peak flow reduction as if we placed it more upstream in drainage area 6. We can get like 14.5% reduction. And this is because they have two very different types of concentration. The water from downstream is going to reach the outlet much faster than the water from upstream. And the water from upstream, this orange, it kind of synchronizes almost exactly in space with the overall watershed runoff hydrograph. And so it tends to perpetuate your storage improvements, even though the lid storage time in green is way longer than all of this. It takes like 11 or 12 hours for all the lid features to fill. So in both design options, you're gonna get some peak flow reduction, but your better bet is to move it upstream, and we can only understand that without doing a bunch of modeling by understanding these general timescale properties. And so the key takeaways of this part of the research are that we kind of affirmed that urban hydrologic performance, at least in lid-influenced basins, is indeed governed at a very high level by these three interacting scales: the storm duration and intensity, the location and size of your storage infrastructure, and local topography. So we confirmed it by using this robust bottom-up modeling. And when we fail to account for these scaling effects, we will propagate uncertainties in our peak flow reduction efficiency of lid, thereby limiting widespread adoption. And a simple scaling framework can identify these hydrological regimes where location controls are shaped by topography and bounded by these storm controls. So that was one part of the research. There's added values in the paper. I'll just summarize quickly here, but we don't have time to go into them in detail. But in addition to just confirming something that's already been published, we also added value by demonstrating how to estimate these characteristic timescales without requiring 350 SWMM models. So I demonstrated if we just use GIS to calculate our time of concentration, there's like 30 different ways you can calculate time of concentration in the literature. And I analyzed all of them and found which one was closest to what would work within the framework using just some readily available geospatial data sets such as land use, impervious cover, soil, slope, and topography. Ran those back through the simulation and got reasonable results. And then I also demonstrated in the original paper, they didn't know how to identify where TR and TC start to change. They said it was kind of a fuzzy boundary. If your case study is firmly within one of those four boxes, you're fine. But as you start transitioning toward the other boundaries, that governing mechanism could start to take over. And I said, well, that's not going to be useful to any engineer because they want to know exactly when's my storm going to be too strong, right? Or when is location going to start playing a role. So we used some equations that are based on peak flow reduction efficacy, and we demonstrated how beforehand you can identify where the TR and TC transitions will occur. And this was really interesting and important because, at least in our case study, the TR bounds between trivial and everything else occurred at about 0.6, and the major storm transition zone was about 1.5. So we further simplified our equations to demonstrate how, if you know these transition zones, you can relate your engineering design, which is just the storage volume and treatment area, to your precipitation volume. So just knowing this at a super high bird's eye level view, you can say for any precipitation volume P, as long as my design is less than 0.6 of this number, I should be fine. I can stick lid anywhere and it'll be fine. And for any precipitation value that's greater than 1.5 times my engineering design, I'm not going to get any peak flow reduction. So it's a really quick way of doing a cost-benefit analysis, especially from the decision-making standpoint, without having to invest in robust software and engineering. And then further, because we wanted to make sure this works under variable storm conditions and not just design storm conditions, I ran another 110 models using a year's worth of spatially distributed variable storm events to assess if the framework held, and it did. So those are added values in the paper. If you have any questions about those, let me know. But what does this mean for looking forward and big picture research? So I think the lowest hanging fruit from this kind of research is that when we reduce uncertainty, we can have improved decision making. So in Houston right now, the way that we decide where to put flood infrastructure projects is we look at areas of historical flooding, so 311 calls, FEMA repetitive losses, maps, that kind of thing. And then usually there's some council district member that has a pot of money and they decide, okay, this neighborhood keeps flooding, I have a pot of money, now I'm going to hire the firm and invest in the robust flood modeling. So we call this worst first planning, but that doesn't necessarily mean that's going to be the best place to stick your solutions. And so I think when we understand LID from a much higher level, especially from these scaling properties, we can start to look at the entire region, the entire watersheds, and make more educated and practical decisions instead of doing this overlay method that seems to be so common. Also, this kind of work should enhance our capability of doing convergent science. So because LID and urban greening is so multifunctional across social and environmental domains, when we have a better understanding of the predictability component of that hydrology circle, then we can better integrate it into convergent science partnerships. So for things like urban heat island reduction or water quality or increasing physical health, if we can be really firm in our understanding of the hydrological predictability from a really high level, then this will eventually enhance our capability of this convergent science. And then also, as hydrometeorological extremes are changing, our design regulations will change, and that matters to adoptability. So this is just a picture of the NOAA Atlas 14 precipitation duration frequency curves from 2018. But since then, they've already released a whole nother volume 12, and they're set to release volume 13 later this year. So every time the design storms change, we have to change all of our engineering, and we can no longer rely on old models or old designs or case studies to inform our current decisions. We need an understanding of what's really going on from a process level to optimize within urban environments, particularly as these extremes are constantly evolving. And then lastly, looking forward, this is a little bit of my research pipe dream, but I think as we start to maybe go back to the kind of research we did in the latter half of the 1900s and look at these scaling generalities, this will really help us bridge across different disciplines. So it's not, of course, just hydrology or climate science that has unique scale interactions. There's also a lot within organizations, within computational systems. Social science has different kinds of scales. Part of my research at my last postdoc was on network theory and looking at how that changes over scales when you're working with decision-making institutions. And so when we combine those space, time, and organizational scale patterns, we can start to get deep learning, we can start to adapt to changing environments, especially in complex dynamic systems. And so with that, I will take questions.
Thank you. Very fascinating talk, and we'll take questions from the room and online.
I got lots. Hi, Cindy. That was a really good talk. Thank you. I enjoyed it a lot.
Mic's on.
Secrets. Yeah, just to repeat that for online, it was a great talk, and I really enjoyed it. Thank you. And I guess I'm going to sneak two questions in if I can. The first one is there like a tipping point phenomenon here. And if you think about like, if you have a sink in your house and the faucet is, you know, a foot in diameter and the drain is an inch in diameter, you could take 20 shot glasses, but you're still going to have a sink overflowing. So what if you just made everything in the city lid compliant, right? Like the whole region was that way. I gotta think that would make a difference. So there must be some tipping point where it's just like if you have enough coverage in there, and maybe the follow-on question you could answer is, are you thinking about, you kind of hinted at this, but are you thinking about like all the other societal benefits of the greening that you cited at the beginning? If you start casting the value proposition and the cost proposition in terms of it may or may not help with flooding depending on the storm, but it also, you know, saves worker productivity and health and medical and all that. So sorry for 2 questions.
Those are great questions, yes. So the second one, I tried making that case with the Houston stakeholders. I think the way the design regulations are set up there, it didn't seem to be a great selling point. I think it needs to be more upstream, where like the government makes those decisions. So I think over time, having these conversations and having this convergent science and demonstrating it will move that forward, because it is, if you look, especially at human health, that's what some of my last research focused on, is demonstrating how to cite it not only for stormwater runoff and storm quality benefits, but at the same time maximizing where people tend to be the sickest and where they could benefit the most from more proximity to nature. You save so much money. And so, yeah, I think that just requires more conversations, but I've tried doing some research to practically show how to do that as well with numbers and models. But the first question you asked, where's the tipping point? I think that's why identifying these transition zones and not just calling them fuzzy, for me, is like my most exciting and favorite part of the new paper, because that does tell you the treatment area. What's the maximum you need to put? How much do you need to treat? 20% of your watershed or 90%? That's going to be a huge difference to get it, but your P is going to change, right? So some people want to just get this much, a few inches of stormwater, and some want to try the whole thing. But it will help you understand how much you need to spend and how widespread, because I don't think it's going to be where we can just say, we'll put it everywhere you possibly can, maybe in Boulder, but most cities are not going to do that because of cost. And so I think identifying these transition nodes ahead of time, hopefully, if this becomes a thing and people adopt it, I think will really help answer those questions meaningfully, hopefully.
Thank you.
Yep.
Try this.
Thanks, Cindy. That was a great talk. So your design storms were catchment integrated, if I understood, right? And then you tried it with some catchment distributed rainstorms, and you got results that sort of more or less matched your, if I understand your theory correctly, did you see those other more spatially distributed values going more into encouraging more location irrelevant regimes? Because now you've got, storms that are falling different locations that are not homogeneous across the catchment, right?
Well, actually, I think I deleted my back-end slides. Oh, no. But instead of running, SWMM is such a cumbersome software, so instead of running all of them for the variable one, I only ran between the least effective, which was drainage area 2, and the most effective, which was drainage area 6. And so I was focusing mostly on location dependence. What I found whenever I looked at the variable storms, it still spread pretty well over the curve, like the design one. But I saw more, there's a 5th regime I didn't cover in this presentation because I didn't want to confuse y'all. There's a 5th regime where if the time of concentration is really high, it's called the dispersion regime. And so your effects disperse widely over time and space, and you still don't see any impact downstream. And I saw a lot more dispersion effects in the spatially variable storms, and I saw none in the design storms.
Okay. Yeah, that's interesting. One more, go ahead. Well, one more quick question. I mean, having gone to Rice and knowing those streets just get swamped during those big storms, right? I mean, there's that big intuitive sense of, boy, I just want to get that water out there away as quickly as possible, right? And so it seems to me that you can only implement this on a sort of a larger municipal level where you can really encourage larger scale thinking.
Yeah.
But how do you overcome that resistance, right? Because, I mean, it sounds like all these lids, after they fill up, then it acts like your typical, gray water effluent flows, right? So,
Right.
But still, how do you encourage to get over that bias of just wanting to get the water out of there, as quickly as possible?
So Houston's unique in that streets there are designed as part of the conveyance network. That's not typical in most cities. Because we don't have enough slope to build enough channels, we make our streets channels. So anytime there's a 2-year storm, which is 2.4 inches over like an hour, that's not that strong of a storm. Every time, the water is designed to go up to the gutter. And people always say, y'all, what are y'all engineers doing? You're not designing our streets flood all the time. But we would rather it go up to the gutter line than to go into your home. But like you said, because it's designed that way, if you put one green roof, it's not gonna change your gutter line hydraulic grade at all. That's right. You have to do that in mass. And so because during my PhD, I was working at the city of Houston and they were making these bigger picture decisions, I was hoping if we could reduce this scientific uncertainty and then you work with like the big decision makers, they can then mandate or strongly encourage downstream, but I don't know if it'll play out that way.
All right, we have a question online from Matthias Steiner. Thank you for the insightful presentation. My question is related to the conceptual regime zones and how they may vary seasonally.
Oh, great question. Well, Houston doesn't really have seasons, so even though I did study a year's worth of data, I didn't compare it to seasons. This could be done elsewhere and see if seasonality plays a role. That would be interesting. But the storms kind of do the same stormy things in Houston. A little different in the summer, but not that much.
Oh, yeah.
Yeah, thanks, Cindy. Great presentation. I was just wondering, earlier in your presentation, you showed different types of low-impact development, from rain gardens to detention ponds. And, it sounds like you tested your model using rain barrels primarily, and I was just wondering how would the results translate to a different region, let's say where rain barrels are not allowed and the different type of green infrastructure or low-impact development could be used.
So intuitively, I think as long as you can still calculate that TS timescale, it should still be valid. It's just a little bit harder when you're bringing in stuff with vegetation because you don't only have the vegetation, you have soil, and then typically under that they'll put rocks, and then they'll put some kind of geogrid fabric, and then there's an underdrain sometimes. And if there is an underdrain, it connects to your urban stormwater network, and that's a whole other way of modeling than if it goes into the ground, right? And so that is a next step question, but I would hope that maybe someone could adopt this to a case study where they assess that. But theoretically, if these are true governing phenomena at like a super high level, it drives how the hydrology works, then as long as you understand that TS timescale, it might be harder to calculate than in a rain barrel. As long as you can identify that and compare it to the other timescales, the framework should hold up, but I didn't prove that.
Great talk, Cindy. I actually have two questions. One is related to feedback, because all your work and real world work is very fascinating. And when a storm comes and how we respond using the lid approach. But there could be another component when you deploy such large scale lid, you have a feedback to the atmosphere that's changing the storm cloud and frequency or intensity. Mm-hmm. Has anybody actually looked into that, and at what level and what scale that actually would play a role? That's the first question. Okay, you can answer it right now, and I can save my second question. Or if you want, I can dump the other question right now.
Oh, I was just going to say, no, but that sounds fascinating and a very RAL type research. So if anybody wants to study that with me, I'm open.
Great. Second question is, you mentioned there are other cities actually adapt the lid approach more readily or proactively, such as Beijing. I'm curious, what the scale, the policy actually, or this approach being applied in Beijing, and has any study look into the impact of that? Or yeah, just curious, because every year I have to stop in Beijing for a couple of days, even though that's not a stormy period. But I really want to hear from you or others about kind of the details of the Beijing situation.
Yeah, thanks. So I don't really know much about the Beijing one, but in the talks I had with the leaders of other US cities that had adopted, it seemed to me, because I was always asking them stormwater questions, it seemed to me they were able to convince their constituents to spend more money on it by making the argument Tim just made, that it's multifunctional benefits. And so they were looking at, yeah, we're fine if the stormwater volume's just a little bit, but we also really want to improve urban heat or air quality, et cetera. And so I think those municipalities that are like more progressive thinking in that way, they're already ready to adopt, but more for the cities that are hesitant, reluctant, and they want to see the stormwater performance improvement, that's when this framework, well, and just in science in general, I think it would help explain discrepancies between case studies. But yeah, I would be interested. I know Beijing has a lot, Denmark, Singapore. There are several places in the world that are expanding. From my latest literature review, it seemed to be mostly in developed countries, but within the last 2 years or so, they're starting to see really rapid interest in this kind of thing in like Latin America and Africa, because they're also interested in these multifaceted, especially with heat, trying to offset the impacts of heat.
All right, we have time for one more question. If not,
I can ask one more.
okay, well, one last question.
Was there anybody else? So sorry, I'm getting greedy with the questions, but so usually if you allow nature to do its thing, it will find an optimal, elegant, simplistic solution to everything, right? So have you tried to de-Houston Houston as sort of a optimal limit of what would be possible? In other words, what would happen if there was no Houston? What would the flow at the outlet be? Because that strikes me as being the ultimate lid, right? Mm-hmm. Yeah. So that would be kind of an interesting simulation to just see, eventually you're going to get a rainstorm and it's going to flood no matter what the surface is, right? Mm-hmm. So that might be like an upper bound of what you might ever even hope to achieve with the best, because all of the lid solutions are in one way or another trying to mimic some natural function.
Mm. Yeah, that's true. That could be the maximum. But Houston's already there, and so we need.
No, but I mean, it gives you an efficiency limit, right?
Yeah. And I think that's been considered, and they've just decided it's too expensive. We can't maximize the entire area.
Yeah, that's not a practical consideration. It's driven by curiosity.
Yeah.
And again, it just says a limit. Like, all right, if we invest in making 40% of it a lid, that gets us 90% of the way there.
But actually, that might not be an upper limit, because like in Houston, it's very clayey soil, so there's still pretty strong surface runoff even in a complete natural prairie. And so when you engineer the storage, you could get longer retention times, actually, theoretically. Yeah.
So yeah, if we had $600 trillion to work with for Houston, I still don't, was there anything we could possibly do to prevent flooding in a situation like Harvey?
I don't think so.
Yeah.
Yeah.
All right, well, that was a very fascinating talk. Let's thank our speaker again. And I forgot to mention, you know where to find Cindy. Thankfully, she's with us here, so you can talk to her anytime about exciting collaboration opportunities.
Thank you.